Hello everyone, I'm Longfei Yin. I'm here to present our work, ratesplitting multiple access for multibeam satellite communications. This is a joint work with my supervisor, Dr. Bruno Klux. Here is a brief outline of my presentation. Firstly, I will introduce the background of multibeam satellite system, conventional multigroup multicast beamforming, and the basics of ratesplitting multiple access. Then I will introduce the system model including satellite channels, a novel beamforming strategy based on ratesplitting, and CSIT uncertainty. Then a maximum fair problem will be formulated and solved. And finally, I will show some results and conclude this paper. As is known that satellite communications will play an important role toward fulfilling future communication demands, such as anytime, anywhere connectivity and huge throughput enhancement. The ubiquitous coverage, together with the efficiency of SATCOM's broadcast nature, has clearly been its main asset. Recently, multibeam satellites have received considerable research attention due to its full-frequency reuse across multiple narrow spot beams. Since the available spectrum is aggressively reused, interference management techniques should be employed. According to the state-of-the-art technologies, each spot beam of the satellite serves more than one user simultaneously by transmitting a single coded frame. Multiple users within the same beam share the same precoding vector, since different beams illuminate different group of users. This promising system follows the physical layer multigroup multicast transmission. Additionally, the multibeam satellite system suffers from several challenges, namely the perfect available power constraints, CSIT uncertainty, and overloaded regimes. In the conventional multibeam multicast beamforming, each user decodes its desired stream while treating all the residual interference as noise. For example, we consider a system with K1 antenna users. These users are clustered into M multicast beams. Distinct contents are simultaneously transmitted to each beam. We denote the symbol streams S1 to SM. P is the precoding matrix. So the received signal and beam rate can be expressed here. All the interference are treated as noise. We call this conventional scheme no-RS in this work. It has the benefit of reaping full degree of freedom in underloaded regimes with perfect CSIT. Secondly, its precoder and receiver complexity are very low. However, this scheme is not suited to overloaded scenarios. The interbeam interference can only be eliminated when the transmit antenna is sufficient. Secondly, it relies on the quality of CSIT severely. Imperfect CSIT is detrimental to the system performance. Spurred by such limitations, let us see the basics of ratesplitting multiple access, a promising interference management strategy for multi-antenna networks. The basic idea is to split messages into common parts and private parts. It relies on one layer or multiple layer linearly precoded ratesplitting at the transmitter and successive interference cancellation at the receivers. As a result, the interference is partially decoded and partially treated as noise. Here are some existing works of ratesplitting based on a wide range of multi-antenna setups. The framework of RSMA enables it to contain space division multiple access and non-orthogonal multiple access as special cases. Benefits of both strategies are combined, for example, in the perspective of spectral efficiency, energy efficiency, and degree of freedom. Moreover, RSMA is robust to the diversity of channel strengths and directions, CSIT inaccuracy, and network load. Motivated by these benefits, So what if we apply ratesplitting multiple access to multibeam multicast beamforming? Then let's see the system model. We consider a Ka-band system with a single geostationary orbit satellite serving multiple single antenna users. Single feed per beam architecture is employed in this system. The downlink channel matrix between the satellite and terrestrial users can be denoted by H. V is a matrix composed of receiver antenna gain, free space loss, and satellite multibeam antenna gain. Its N-case entry is modeled here, where the GNK is the multibeam antenna gain from the N's feed to the case user. Moreover, the ring fading effect and signal phases are characterized in the matrix Q. There are M messages intended to each beam, in line with the multicasting of frame-based precoding. Each message is split into a common part and a private part. All the common parts are packed together and encoded to a common stream at C, while all the private parts are encoded into private streams. The precoding matrix P is a NT by M plus 1 matrix. Then we obtain the transmitted signal and the signal received at user K. At user size, each user firstly decodes the common stream at C by treating all the private streams as noise. After the common stream is decoded and removed through SIC, each user then decodes its desired private stream by treating all the other interference streams as noise. The beam rate is composed of a common rate portion and a private beam rate. Imperfect CSIT is also considered in this work. To model CSIT uncertainty, channel vector H is denoted as a sum of the channel estimate and the CSIT error. The CSIT error variance is allowed to decay as p to the power of minus alpha, where alpha is the scaling factor which quantifies CSIT quality. For a finite non-zero alpha, CSIT uncertainty decays as p grows by increasing the number of feedback bits. In particular, we truncate the value between 0 to 1 in this work. Alpha equaling to 0 means a non-scaling CSIT with fixed number of feedback bits. Alpha equaling to 1 corresponds to perfect CSIT in the DOIF sense. To formulate a maximum fair problem with imperfect CSIT, a stochastic average rate framework is adopted. The stochastic average rates are short-term measures which capture the expected performance over CSIT error distribution. For a given channel estimate, we construct a realization sample. These realizations are available at the transmitter and can be used to approximate the average rates through sample average functions. So the maximum fair problem is formulated. The first constraint ensures the common stream to be decoded by each user. The second constraint implies that each portion of the average common rate is non-negative. The third is the per-feed power constraint. It can be seen that this is a non-convex optimization problem. A modified weighted minimum mean square error approach is designed to transform the original problem into an equivalent problem based on the rate and WMMSE relationship. Considering the block-wise convexity, we use alternating optimization algorithm to solve this problem. Variables in this equivalent problem can be optimized iteratively until convergence. Each iteration contains two main steps. Firstly, as shown in step 4, all the equalizers and weights are updated according to a given precoding matrix obtained from the previous iteration. Then we fix the equalizers and weights, and update the precoding vectors as shown in step 6. Note that step 6 is a convex optimization problem, which can be solved by the CVX toolbox. Now for the simulation results, it can be seen that RS outperforms non-RS in the whole range of per-phase available power due to its more flexible architecture for non-orthogonal transmission and robust interference management. For perfect CSIT, RS achieves around 25% gains over non-RS. For imperfect CSIT, RS is seen to outperform non-RS with 31% and 44% gains respectively when alpha is 0.8 and 0.6. Accordingly, the advantage of using RS in terrestrial networks is still observed in multibeam satellite systems. Through partially decoding the interference and partially treat the interference as noise, ratesplitting is more robust to the CSIT uncertainty and overloaded regime. Such benefit exactly tackles the challenges to multibeam satellite communications. This figure shows the influence of a wide range of CSIT quality on both strategies. For a specific power, as CSIT error scaling factor drops, the maximum failure rate gap between RS and non-RS increases gradually. So the gains of our proposed rate-splitting scheme become more and more apparent as the CSIT quality decreases. Additionally, all the users within a beam share the same precoding vector. The beam rate is determined by the user with the lowest SINR. Considering 2, 4, 6 users per beam, it's clear that increasing the number of users results in system performance degradation in both RS and non-RS. In conclusion, this paper considers a novel multibeam multicast beamforming based on rate-splitting multiple access. A per-phase available power constraint maximum fair problem is formulated with imperfect CSIT. A modified weighted minimum mean square error approach together with an alternating optimization algorithm is developed to solve the optimization. And finally, RSMA strategy is shown very promising for multibeam satellite communications compared with the conventional approaches. Here are some references. Thanks.